Hey everyone, welcome back to another session with OneClass. Today we're going to be going through some math problems at the high school and university level. My name is Bassam, I'm an engineering graduate, and we'll start off with the first question over here. Okay, so this question is asking us to circle to indicate whether each statement is true or false, and it gives us two statements. So I'm going to open up this image file to help us figure out what those statements are. So we'll save that over here and we'll open it up. Okay, so this is what we're asked. Circle to indicate whether each statement is true or false and justify your answer. So our first statement, if f at x is a differentiable function, then d at dx, or the derivative of f at square root of x, is f prime at x divided by 2 square root of x. So we need to verify if this is true, and then we'll go through the second problem as well. So we'll start off with writing out some givens. So we're trying to see if this statement is true for f at x when it's a differentiable function. So does this equal f prime at x, or the derivative of f at x divided by 2 square root x? And we'll put a question mark. Okay, so one way to think about this question is to kind of define f at x as some function. So let's say we defined f at x as x cubed, or it could really be anything. What we could do here is test out if the statement is true for, let's say, if we substitute, we know this is a differentiable function, so if we were to substitute f prime square root at x, would we get this as follows? So let me erase this. So we know f prime at x for this function will be 3x squared. And we know if we substitute for f prime square root at x, if we substitute that in, we'd get 3 square root at x squared, and this would give us 3x. So knowing this, we want to think about, let's say we looked at this equation over here. Can we use this to get the same values as we calculated here? So if we had the derivative of f, if we substitute f at x, so here, or square root x, so if we substitute f square root x, this would give us square root x cubed, which would be x 3 over 2. So this is one component, so this is the inside component over here. So using this equation down here, we know that the left side will be the derivative of d dx of this function. So this is what we calculated. So we would just plug this in. So x 3 over 2. So x 3 over 2. Does it equal? So we'll substitute in f prime at x. So 3x squared. And then we have divided by 2 square root x. So on the left side we would have 3 over 2x to the half. And then on the right side, if we multiply both top and bottom, so we'll multiply both top and bottom by square root x to get rid of the square root at the bottom. So, and this will give us 3x squared square root x divided by 2x, which would give us 3x square root x, which would be, so 3 over 2 actually, and this would be 1 plus a half. So this would be, so this would actually be, we'll combine these two variables, so we would end up with x 3 over 2. So we can see that this does not equal this. So we can see that the exponent here and this exponent is not true, so this is not equal. And we know that this does not hold true. Another way to think about why this statement is false is as follows. Let me clear the board over here. So what we can think about here is if we just took the derivative, so of f prime at x, so if we took the derivative of this, we know it would be, so sorry, if we took the derivative of f at x, we know that would be the derivative of the function square root of x, so the derivative of this multiplied by the inside. So we usually what we do here is the derivative of the outside, so f prime at x, f prime at square root x, and then the derivative of the inside, which would be 2 square root x. Or to make it a little simpler or easier to understand, it will be multiplied by 1 over 2 square root x. So if we had, so the derivative of this would just be a half x minus 2, which would give us this. And then we can see here that the top, the numerator, should not have been f prime at x, but it should have been f prime square root of x, because usually when you're taking the derivative of a function within a function, what you should be doing is the derivative of the outside function divided by the derivative of the inside function. So, and that's kind of another way of thinking about why this statement is false. So part A we know is false. So we'll look over here. Let's go through quickly what the junior tutor said for part A. So 6a, the given function is blank. So here there's no real, there's a lot of gaps in the solution. Seems like there was an error translating the solution into OneClass's website. So there's no real solution. Similarly for B, let's go through B actually. Okay, so statement A is false. Let's look at statement B. So here it's saying if a circle is expanding and its radius is increasing at a constant rate of 2 centimeters per second, then its area is increasing at a constant rate. Note that area is this, true or false. So is this true? So if the radius is increasing at a constant rate of 2 centimeters per second, does it mean that the area is also increasing at a constant rate? So we'll write out some equations to figure out how to think about this. So the first equation is just the one given over here, area. So this is question number 1. This is the first question we're going through, part B. So area equals pi r squared. And essentially what we're saying is the radius is increasing per some unit of time. So we could represent r as the following. So we could say r is some constant times t, where t is just time in seconds and is multiplied by a constant. This is an equation for, you can kind of also think of the simple format, which is y equals mx plus b. So here r is our y and x is our t, and we can see that this is a linear equation, and the rate is increasing at a constant rate. So we could substitute for c equals to 2, or any rate, it won't really matter, but we'll define it as such. And let's think about let's substitute this in and see what happens to the area over here. So if we substitute it in, we would get area is pi ct all squared, which would give us pi c squared t squared. So here we know that the beginning terms, these are just constants, so we just some number if we were calculating it, and t here is our variable, which is squared. So right away we can say that because t is squared, it would not be increasing at a constant rate. So area would not be increasing at a constant rate because its equation here is raised to the power of 2. So it would be in a plot would look something like that, versus CT would look something like this, and constant rate is this. So here once again, if we think of y equals mx plus b, so m is our constant here, plus b. X is just t, a is just y, and here we know that x is raised to the 1. This is the linear equation. Since t is squared, it's not a linear rate, so it's not increasing at a constant rate. And we can say that area is not increasing at a constant rate. So we can also say for b, the answer is false. So let's go through with the junior 2D set. So the given function is f at x, which is differentiable. So for a, we already said that didn't really make much sense. So for b, if the radius of the circle is increasing at a constant rate, its area is increasing at a constant rate. False. Reason: the area of a circle. So we're present. Okay, so this is an incomplete answer to the question, but we went through the question step by step, and we know that both statements are false. So we'll say incomplete answer. Both statements are false. Excuse me. Okay, so yeah, we'll mark this as incorrect, and we'll move on to the next